propulsion team. So this is one of our combined projects, and so now Vidar Aerospace will tell you about their fighter.
Thank you, Dr. Ashworth. Good afternoon, everyone. I'd like to welcome you on behalf of Vidar Aerospace to our final presentation for aircraft detail design. For the duration of this presentation, the screen above me will be our primary screen, or screen A, while the screen off to the side will be our secondary screen, or screen B. I'd like to introduce everyone here this morning. My name is Michael Galante. I am the design team lead for this project. Joining me this afternoon, I have Andrew Beal, Christina Davis, Nishan Kula, Taylor Knight, Samuel Douglas, Kayla Krolak, Samed Talabatula, and up front here, Mr. Chuhan. To bring up to speed on how we got to where we are today, this project began in the preliminary design phase, where we developed the aircraft's preliminary design with respect to the aircraft's aerodynamics, propulsion, structures, performance, and stability and control. On the secondary screen, you can see our the iterations of our design from our initial preliminary design to our final preliminary design. After this, we then proceeded to detailed design, where we sought to validate the aircraft's preliminary design, including the internal structure, and we sought to evaluate the performance of our original test model. After testing, we then began recommending modifications, which were then evaluated, and then a final decision would be selected for our flight test article. On a secondary screen, you can see our initial primary design, our preliminary design, as well as our original model and our modified test model. I'd like to begin with a brief introduction and motivation for our project as a whole. Vidar Aerospace was tasked by the Department of Defense to develop a lightweight air superiority fighter. In response, we have proposed the Vidar Wraith, which comes in at a maximum gross takeoff weight of 38,000 pounds. The aircraft is powered with a twin-engine, Pro-Elliott-designed F-215 engines, which are capable of providing approximately 70,000 pounds of thrust. This would result in a revolutionary design with a thrust-to-weight ratio of 1.85, which is far in excess of what is currently seen in modern fighters with a thrust-to-weight ratio of 1.3. For our motivation, we did seek to fill a gap in current military capabilities where there are currently no lightweight air superiority fighters in service with the United States military. In addition, this revolutionary design would seek to fulfill current fighter development programs, which are seeking fighters with that higher thrust to weight. For an overview of the remainder of the presentation, we will begin with mission specifications and mission profile for the Vidar Wraith, followed by our analysis, model development, our wind tunnel test, and our wind tunnel results for both the original and modified models, before proceeding to our preliminary structural design analysis. We'll then look at some market analysis, our labor accounting, before ending up with some conclusions and recommendations, before opening the floor for questions and answers. We'd like to begin next with mission specifications and mission profile. Per the request for proposal that was issued by the Department of Defense, the aircraft must be capable of a few mission specifications. Among these, the aircraft must be capable of Mach 1.2 flight or greater at an altitude of 30,000 feet, while being capable of maintaining steady level unaccelerated flight, or SLUF, at an altitude of 45,000 feet. The aircraft will maintain a combat radius of at least 200 nautical miles, at which point it must be capable of performing a 30-minute combat air patrol. Should the need for combat arise, the aircraft will be capable of a 3-minute combat engagement with 1 minute at maximum G-loading. This G-loading has been predefined as 9 Gs at sea level or 5 Gs at an altitude of 30,000 feet. Additionally, the aircraft must be capable of launching from both a traditional runway and an aircraft carrier. While maintaining that maximum gross takeoff weight of no more than 38,000 pounds. This includes an armament of 2 radar and 2 heat-seeking missiles, as well as a 20mm cannon. In order to meet all these criteria, the typical mission profile was developed as shown on the primary screen, where the aircraft will begin by climbing to a cruise altitude and cruising out to the edge of its combat radius. The aircraft will perform its combat air patrol with the ability to engage any enemies should the need arise. The aircraft will then cruise back, land, taxi, and shut down. To begin with the original model development, I'd like to introduce Andrew Beal.
Thank you, Mike. Once again, I'm Andrew Beal, and I'll be going over our original model development. So this is an introduction to our model. It's a 1:25 scale model built out of 7 3D printed parts and 25 metal components. And excuse me, once we assembled it, we just applied a quick surface finishing, essentially just sanding and painting to give a nice smooth finish. So when determining our scale for our model, there are 5 considerations we had to take under consideration. First off is budget. We had to be under below $550. We had to have a maximum applied force of 40 pounds on the balance. We had to have no greater than 7%, no greater than 7% blockage in the wind tunnel. We had to be considerate of wall effects, and we had to make sure that our aircraft was strong enough to withstand lifting forces acting on it during testing so it would not fail. So here you see the exploded view. Like I said, there's 7 3D printed plastic parts, 3 for the fuselage, 2 for the wings, 2 for the empennage, and 25 metal components for the structural reinforcement. Primarily there are rods throughout the lifting surfaces. In addition, we also have the mount and the leading edge extension plate because at that point in the aircraft fuselage, the plastic's too thin, so we had to reinforce it with some metal. Again, you have the exploded view here with all the labeled components as I just identified. And then here you have the ghost view. You have the 3 view above my head and the isometric view on the secondary screen. As far as our wing structure goes, each wing is held in place by 2 1/8 inch rods. And the empennage though is a little more complicated. It's got 2 rods in both the horizontal tail and the vertical tail before being attached into the empennage with a 1/4 inch rod. Once everything is assembled, you have all the attachment points on the primary screen, and on the secondary screen you have a view of our original model. The last thing we had to do before we tested was test the structural integrity, just make sure our aircraft would not fail during testing. To do so, we applied up to 40 pounds, which is the expected load, or maximum allowable load on our aircraft. Applied up 40 pounds to the wings and 5 pounds to the horizontal tail. Now I'd like to introduce Christina Davis.
I'm Christina Davis, and I'll be going over the wind tunnel test equipment used. We used the AeroLab 87 series closed circuit wind tunnel for testing as depicted on the secondary screen. We used this wind tunnel due to its large test section of 32 by 45 inches. The tunnel is capable of speeds of up to 240 feet per second due to its 125 horsepower motor. We were required to meet, like Andrew said, the 7% tunnel blockage. Due to this, we have a 1/25 scale model of the race. We used a 6-component pyramidal balance that was able to withstand a maximum loading of 50 pounds with an accuracy and repeatability of up to 0.02 pounds. We used it along with the data acquisition code to record our aerodynamic forces and moments. We set the side slip angle manually while setting the angle of attack by inputting our desired angle of attack into the computer program and allowing it to adjust. We used the LabVIEW 8.2 acquisition software. We also use white contests for flow visualization, along with 2 black lights in the wind tunnel test section in order to create a bit of a contrast between the model and the wind tunnel itself. Each contact was 1 inch long. Now I'll be going over the wind tunnel testing for the original model. We had 4 test configurations. For each configuration, we used at 82 feet per second wind tunnel velocity. We chose to use this velocity by setting our model to the highest angle of attack and then increasing the velocity until we saw aeroelastic effects on the wing. We ranged our alpha sweep during testing from -4 degrees to 30 degrees and our beta sweep from 0 to -10 degrees. And again, the flow visualization was performed on the model with the 1 inch tufts. As you can see on the primary screen, the secondary screen, we have our 4 model test configurations. On the primary screen, we have our original model test configuration and our tail-off test configuration. On our secondary screen, we have our fuselage-only test configuration and our tucked-in model configuration. Again, we use the 6-component pyramidal balance along with the data acquisition code to record our data. For the flow visualization, we used 2 GoPro cameras to record. First, we recorded our data at 0 degrees angle of attack and 0 degrees side slip before recording any data. We then recorded our data for all increments of angle of attack and all increments of side slip. We did this for each test configuration. For flow visualization, we only used our tucked-in model. From our data, we wish to create 5 plots, one being lift versus angle of attack, one being lift versus drag, another being pitch versus angle of attack, and then roll versus side slip and yaw versus side slip. From our data, we also wanted to determine our lift performance parameters, our trim angle of attack, and our static stability derivatives. We also wanted to determine our drags so that we can create our piece of S and first required plots. For our data, to reduce our data, we first subtracted our tear data from our data obtained and then created the plots mentioned previously. For our flow visualization data reduction, we watched the recordings from the GoPros and only focused on any instances where the flow was disturbed in any way. Now I'd like to introduce Michelle.
Good evening, everyone. I'm going to be going over the performance of the Vidar Wraith. On the primary screen here, you have the CL versus alpha plot for the Vidar Wraith. This has been adjusted for a 3-degree correction. When we mounted the Vidar Wraith onto the balance, we noticed that there was a -3 degree angle of attack that was on the model. So this plot above you has been corrected for that. You should note that the original model without the tufts and the original model with the tufts have similar trend. It is important to note that at 14 degrees angle of attack, the wing of the Vidar Wraith installed. However, we still produced lift. This was due to the fuselage, which was able to produce lift all the way to 30 degrees angle of attack, as you can see from the plot. The reason why we only went to 30 degrees angle of attack is because the balance could not go any further. On the secondary screen, we have the drag model of the Vidar Wraith. We have an increase in our drag. This is for the original model with tufts and original model without tufts. This is due to our inlets being flow-through inlets. They're also S-shaped ducts. This generates more drag than we could predict. Also, we noticed during around 12 degrees angle of attack that there was a significant amount of separation that was occurring above the inlet and near the fuselage, which we could not predict as well. On the primary screen here, we have thrust available, thrust required plots for 30,000 feet. The thrust available plots data was given to us by Pirelli Engineering. This is being corrected for losses for the inlet, as it's not a variable inlet geometry. The thrust required lines are generated from drag values. You see the little bump around 600 knots. This is due to the drag rise. This is the drag rise due to Mach number. As you can see here, that because of the increase in drag, the thrust required for the original aircraft, that is the wind tunnel model, is less than the thrust required for the preliminary model. Also, the vertical line that is around 700 knots is Mach 1.2 condition. This is a requirement in the RFP that we have to meet to say that we can cruise faster than Mach 1.2 at 30,000 feet. On the secondary screen, we have the piece of S plot for the preliminary design versus the original model at 1G. Piece of S is specific excess power. It's the aircraft's ability to change its energy state, that is, either perform a climb or increase its velocity. As you can see from the plot and our early sheet design of thrust of 1.85, we have piece of S up to 60,000 feet. However, we will not be flying at 60,000 feet. On the primary screen, we have our 9G maneuver at sea level. Initially, in the preliminary design, we designed the Vidar Wraith to be able to perform this maneuver at corner velocity. However, due to the increase in drag, we no longer perform the maneuver at corner velocity. However, we still do meet the requirement by sustaining the stern, and that is shown from the thrust available, thrust required plot on the primary screen. On the secondary screen, we have our piece of S plot for the preliminary design versus the original model at 9Gs. This is a range of altitudes. The one we want to look at is at sea level, as this is a requirement per the RFP. And it's to note that we can make this at around 420 knots. On the primary screen, we have the thrust available, thrust required plot for a 5G maneuver at 30,000 feet. Again, in the preliminary design, we designed for the aircraft to perform this maneuver at cone velocity. However, with the increase in drag again, we perform this maneuver around 580 knots. However, it's to note that we still can't perform this sustained maneuver. On the secondary screen here, we have a piece of S-plot with our preliminary design versus our original model. What we want to look at is the 30,000 feet, and as you can see there, we performed the maneuver around 580 knots. I'll now go into the flow visualization. As I mentioned before, we noticed during the flow visualization stage that we had separation occurring right above the inlet lips, and that occurred at 2 degrees, and it continued to show an adverse pressure gradient on the tufts all the way through until the wing stalled. In this case, on the primary screen, we can see that the flow is affected by an adverse pressure gradient at 12 degrees. On the secondary screen, we see the drag rise, that is accounted for the drag coefficient versus the angle of attack. And as you can see, around 7 degrees angle of attack, there's a significant increase in drag, which we could not predict in the preliminary phase. On the primary screen here, we have the flow visualization representing that the wing has stalled at 14 degrees angle of attack. This is denoted by the tufts moving in the reverse direction due to the adverse pressure gradient. On the secondary screen, we have our lift coefficient versus angle of attack, and around 15 degrees we see that little flat line, which is corresponding to that. On the primary screen, we see the vertical tail stalling. It's at 22 degrees angle of attack. We can see this due to the tufts again being affected by the adverse flow. And then on the secondary screen, at 26 degrees angle of attack, we see that the adverse pressure gradient has now affected the horizontal tail as well. As I mentioned before, a big contributor to our lift above that 15 degrees was our fuselage. As you can see, the fuselage is at 30 degrees angle of attack, and the flow is still attached. On the secondary screen, we have the lift coefficient versus angle of attack for the fuselage. We also perform beta tests from 0 to negative 10 degrees. The image above me on the primary screen is the attached flow at a beta sweep of negative 10 degrees. I'll now go into the stability and controls. On the primary screen, we have the longitudinal static stability for our aircraft. We are stable in this condition. Please note that for a fighter, the static stabilities are pretty relaxed and they're pretty close to 0. Therefore, on the secondary screen, if you see, the static margin for our preliminary design was 0.021, and for our original model was 0.017, with a percent difference of 19%, and the percent difference for the CM alpha was 13%. On the primary screen, we have the directional static stability. Again, we are stable in this condition, and we have a percent difference of 12% from our preliminary model. We have a lateral static stability on the primary screen. It's to note that we are slightly unstable in this regime. However, if we take a closer look at the numbers, the original model is at 0.004, and the preliminary design is at negative 0.0013. This is both very close to 0. And in case this does affect the pilots' performance in the aircraft, there will be a control augmentation system or a flight computer to assist them in this. I might like to pass off to Taylor Knight, who will go over the modified model.
Thank you, Michelle. I'm Taylor Knight. I'll go over the modified model development. So going to the modification, we wanted to correct any performance deficiencies that we found from our original model. This includes early flow separation, unable to perform maneuvers at a corner velocity, as well as high drag. To do this, we looked into notched wings, dogtooth, strake, and leading edge root extension. We chose to go with the leading edge root extension because this acts like a delta wing, where it creates a primary and secondary vortice at high angle of attack. It also increases lift by approximately 10% at those high angles of attack. It will reduce wave drag and transonic acceleration, and when it's coupled with high lift devices, it greatly reduces drag and maneuvering. So our leading edge root extension increased the wing area by approximately 25%. It has a leading edge sweep of 52 degrees and meets the exposed wingspan about a third of the way out. This wing modification was designed to fit over the existing model using the existing wing structure. So it has a hood that slides over the original leading edge extension that will act as the root extension. On the primary screen, you can see a 3 view of our structure, and on the secondary screen, you can see an isometric view. I will now go over the wind tunnel testing. So we use the same procedures for our modified test as our original. The only difference is we only tested one configuration, and that was the tufted model. And from our wind tunnel test data, we can see that we increased our lift coefficient and had a slight shift in alpha zero lift. And from our drag, we had a slight increase in CD naught, and we had approximately the same drag at high angles of attack. I'd like to now introduce Samuel Douglas, who will do modified model performance.
Thank you, Taylor. Good afternoon, everyone. I'll be taking you through the performance of our modified model. On our primary screen, we can see the thrust required plot for 30,000 feet. Like it was stated before, we have a requirement for a Mach 1.2 maximum speed at this altitude. This shows that we both meet and exceed it with our original and modified model. On the secondary screen, we can see the piece of S-plot for the original and modified model. We also have the requirement for steady level unaccelerated flight at and above 45,000 feet. This shows that with both models, we do meet and exceed this requirement. However, because our aircraft is not outfitted with life support systems, we are unable to fly above 50,000 feet. We also have a requirement for a 9G maneuver at sea level. We are able to meet this requirement with both models. However, we have fallen short of our goal to make this at quarter velocity. Both models show that at high angles of attack, shown here at low airspeeds, that we come very close to meeting this. However, we never get quite to making this turn sustained at quarter velocity. Our secondary screen shows the piece of S-plot for 9G maneuvers. Here again, you're going to want to look at the sea level line. We also have the requirement for a 5G maneuver at 30,000 feet. This was the primary driver for many of the things on our aircraft, such as the large wing, the moderate taper ratio, the moderate wing sweep, and the revolutionary 1.85 to 1 thrust to weight ratio. We try extensively to get our aircraft to make a sustained 5G maneuver at 30,000 feet. However, we have fallen slightly short. And on our secondary screen, we can see the piece of S-plot for 5G maneuvers. Again, you're going to look across the 30,000 foot line there. Next, I'll go into flow visualization of our modified model. On our primary and secondary screens, we have fully attached flow at 0 degrees angle of attack. We had very little base drag on this aircraft because of this. At about 6 degrees angle of attack, we start to experience rocking. This was seen on the starboard wing. We started to get an adverse pressure gradient and local areas of separation. On the secondary screen, we can see a zoom in of this wing and the flow characteristics shown by the tufts. At 8 degrees angle of attack, we get a wing stall. This was to be expected, as our aircraft is primarily a lifting body. And at 28 degrees, we have a tail stall due to our angle of attack. Our downwash finally caught up with us, and the tail stalled at 28 degrees angle of attack. However, the entire aircraft remained flying up to and perhaps beyond 30 degrees angle of attack. On our primary slide, we show our beta sweep at negative 8 degrees angle of attack. This shows fully attached flow. However, when we increase 2 more degrees, the tail completely separated. Or sorry, the vertical tail separated and stalled. Next, I'd like to introduce Caleb Corlett. We'll go over modified models to landing control.
All right, good afternoon, everyone. Like I said, I'm Caleb Carlock. I'm going to be going over the stability and control analysis for the modified model.
Just as a quick note, we did keep the center of gravities the same so we could do a direct data comparison. As you notice on the primary screen above me, where the red indicates our tufted model for the original model, where we are fully stable. However, with the introduction of the lurks, or leading edge root extension, we do have instability at lower angles of attack, and this is because of that reference point of that leading edge root extension being in front of our center of gravity, causing a pitch up moment. This correlates to about a -5% static margin. And then after the wing has completely stalled after about 14 degrees, where our horizontal tail is still effective, causing the nose down pitching moment. And that correlates to a static margin of about 38% after the wing has stalled. Now for our directional static stability, it's very much the same. This didn't affect the center of gravity that much in that aspect. We still are fully stable for our directional static stability. Now for our lateral static stability, with the introduction of the leading edge root extension, we do become stable. Much of this is attributed to the fact it acts as kind of a high wing, and that does have a stabilizing effect on an aircraft. However, you're looking at the magnitudes, it's very close to 0, indicating that we are basically marginally stable for our lateral static stability. Now I'll be going over the comparison to our requirements. Looking at the primary screen, this is tabulated results of our aircraft mission specifications for our preliminary design, the original model, and the modified model. You notice that we do meet all the requirements and exceed all the requirements that were stated in our request for proposal. Now I'd like to pass off to Sumit Albatula.
Thank you, Caleb. Hi everyone, I'm Sumit Albatula, and I'll be going over the preliminary structural design. Can I have your attention on the primary screen? As you can see, the structural material layout mostly is made of carbon fiber, and then the titanium alloy for the leading edge of the wings, Kevlar at the nose, and the polycarbonate for the canopy. And the secondary screen shows the pie chart of the material. As you can see, about 74% is made of carbon fiber. Moving on to the internal structure and components, as you can see, includes the fuel tanks, the engine, inlet duct, radar in the black at the nose, and everything in there is the internal structure, including the ribs and spars. On the secondary screen shows the bottom view of the aircraft, which shows the location of the missiles. Moving on to the weapons system layout, shows the missiles and the cannon in the red, with which includes ammunition below the pilot. On the secondary screen, you can see the detailed specification of the weapons, which includes the cannon, which includes 1,080 rounds with 2 AMRAAM and 2 Sidewinder missiles. Moving on to the structural VN diagram that requires the CFR 23 requirements with gust lines. As you can see, the Vidar rate is structurally can sustain all the performance requirements. On the secondary screen, it shows the factors that included the structural VN diagram with the minimum maximum Gs with the factor of safety of 1.5, driven by the negative dive speed of gust line. Now I'd like to introduce Chun Han Ling, who's going to go over the structural layout.
Thanks, Ben. So we have already talked about the preliminary design of the structure of our aircraft. What we're going to focus on most is the wing. The wing and the horizontal tail are one of the thinnest sections of the aircraft itself, and it's most likely the location where tail is going to occur. So, using as model, we make some assumptions. First, we idealize the wing section. We assume a circular spar and rib caps. Also, we assume the isotropic composite material for the carbon fiber that's composed the main wing. And that's to simulate the isotropic composite material of the carbon fiber that we are putting on the wing itself. Now we also identify the maximum G loading. If you remember from the previous slides, the largest G loading is 19 turns at sea level, and that's the part we're looking at most. We also assume a factor of safety of 1.5, and if you take a look at the EN diagram previously, you'll notice that gives it about 13.5 G for the aircraft. So, it's very simple. You fix the wing at the root, and then you apply the load. The load we calculate using strength approximation, and that load sums up to be about 256,000 pounds And you can see on the second screen that corresponds to the right line on the purple wing itself. And when we run the ANSYS simulation, it shows the wing deflects to about 9.15 inches at wingtip, and that corresponds to red region on the second wing with the multiple colors. That means that's the largest deflection of the wing itself. Similarly, we do the same thing for horizontal tail, and everything is exactly the same assumption, and we run the test. And the loading is over there. The loading we calculate using the shrink small approximation similarly. We found to be 85,000 pounds, and the maximum tip deflection of the wing is 10.4 inches. So the most important part about the structural analysis is to see whether the wing fails or not. So as you can see from the primary screen, that is the original wing. The original wing without the leading extension. It's not a modified model, by the way. And you can see that we have a maximum stress about 1,100,000 pounds. Now give a comparison. The tensile strength of carbon fiber actually has a pretty wide range, and 480 KSI is pretty large. And you can even give a more conservative number, about 280 KSI. That's also one of the number for the carbon fiber tensile strength. And you can see that 1,400,000 pounds is well within the limit. Similarly, you can look at the more constraining horizontal tail, which is smaller and has about 1,508,000 pounds of KSI on the root of the horizontal tail. That's also under way under the tensile strength of carbon fiber, which the wing and horizontal tail is made of. So we're not affected. So that's some of the whole project itself by looking at market analysis. We use the rent cost analysis method to kind of calculate the whole project for the project itself. So the RDT&E process, that's the research, design, test, and evaluation, costs about $3.53 billion. And the acquisition costs about $5.86 billion. The sum of those two give you the project budget, which is about $9 billion, compared to other currently developed or other newer generation aircraft, which could be about $1 trillion. In comparison, this is pretty cheap, which is one of the reasons we developed this, is to make sure that it can develop quickly and be cheap to operate. And let's look at operation. We estimated to be about $21,000 per hour. Given the estimation of the aircraft lifespan to be of 30 to 50 years of operational lifespan, that sums the total life cycle to be about $38 billion. The cost per aircraft we calculate using simple method, the same red method, is $54 million for production of 25 aircraft at bulk. Now compared to the F-22, F-22 costs about $450 million already. So one of the reasons is that we want to make sure that this is compatible, and we can basically wide production of this aircraft to fill in the current military gap I mentioned in the beginning of the briefing. So to final wrap up, I'll pass it back to Mike Galante.
Thank you, Srihan. I'd like to conclude with this brief labor accounting for our team during this phase of development. Above me on the primary screen, you can see the Gantt chart detailing the milestones that we had developed, that we had set in the development of our project during this last phase. Looking at the hours that our team put into the program, we have the predicted and actual hours shown on the primary screen. The predicted hours take into consideration 2 hours outside of class for every hour inside of class. Presently, we are approximately 150, 200 hours above that predicted line. Looking at the cost per hour category and per cost, engineering tasks have dominated the number of hours that we have put in this semester. Finally, I'd like to wrap up with some conclusions and recommendations. First and foremost, we noted that both models were capable of meeting the requirements set forth within the request for proposal. However, we did not meet the ability to perform our 5 and 9G maneuvers at our corner velocity as our preliminary design had shown. The original structure, meanwhile, did pass structural analysis and did meet all the expected loads that would be seen during flight. In order to correct for these, we would like to first continue further investigation into our design, primarily looking at Our high lift devices that we were accounted for in our preliminary design that we were unable to test during this phase of testing, as well as looking at optimizing the design for a leading edge root extension. Some considerations would be increasing the sweep angle to optimize that design. Finally, because our original structure did meet our structural analysis, we'd like to proceed and test the modified model for its structural integrity before deciding upon a final flight test article. That concludes our presentation. I'd like to open the floor to any questions that you may have.
Good work, guys. I really want to have a couple of questions, but first off, I want to say this one a little bit near your heart. What you guys went through with the leading edge root extension. I worked on something very similar to that in my first job out of school. We were working on a 2C personal jet that had some stall issues, so we spent a lot of time in the wind tunnel going through a lot of different variations and iterations on one of those root extensions. We had a dog tooth in the wing as well, which wasn't really affecting our particular problem. So the fact that you narrowed in on that as being one of your solutions and realized that now go forth and optimize to help you get to where you need to go was cool. So I applaud you guys for that. That was good. I comment at first. I was a little skeptical of your 4.5 pound model load when we were looking at that. So I ran a number and I'm not as skeptical anymore because I came out something pretty close to what you guys did. So that was just for my own edification there. We go to slide 73A. We're looking at an IMG. Is this diagram reflected in an ultimate sense such that it has the 1.5 safety factor in it?
Yes.
Okay. I heard a comment about part 23 being used to guide some of this. Like, can you state that comment again? How was part 23 played into this diagram development?
Well, for the gust lines, particularly, we use part 23, for the rough air gust, the clear air gust. Using those values of 66 feet per second, things like that, that's where part 23 was used.
Okay. Glad to see you guys using that. I think it's a really good piece of guidance. It's not applicable to this airplane. This is an L516 airplane straight through. That would have been just a good piece of information to couch that said, yes, we're using this as some kind of guidance, realizing that for our particular application, it's not directly applicable. Good on you for knowing what you're looking at. One last one, 76A. There's a comment in there about, the slide says the CP distribution was used. What does that mean?
That involves the center of pressure over the wing, the airfoil data.
Sorry, in order to phrase that question, how did you derive it and what load cases it applicable to?
The center of pressure was applied in order, sorry.
I'm curious how did you establish that particular CP distribution?
Oh, okay.
And what load case would it be representative of?
That center of pressure did come directly from NACA data. We did use a traditional NACA 60-40-210 airfoil for the primary wings and a double OE configuration for the horizontal tail and vertical tail.
Did you just pick a zero angle attack point off of that of her? Because the distributional change is a function of angle of attack.
Correct.
So what angle of attack was that representative of?
I believe, yes, 0 to 0.
Okay. Just keep in mind that that's good because it's one of the first I've heard today that actually addresses a torsional loading scenario by putting some kind of a chord-wise pressure distribution on there. Just pay a little bit of attention to the applicability of the particular point that you're combining load cases for. Okay. Good work, guys.
Thank you.
Nice presentation. I'm a little confused though. You guys, and it's mainly related to the things that you looked at for modifying your aircraft after the original model was tested. It seemed like your original model was pretty okay, at least from the data that I saw. And then you had a number of, I think 3 potential solutions that you looked at to modify it. And then you picked the lurks. But what kind of trade studies did you do to justify that selection?
So when we first looked at the the original data, what intrigued us the most was that we couldn't predict the separation that was occurring right behind the inlet on the top. And also, if you look at our wing, the stall occurs towards the inboard side of the wing. So when we looked at the dog tooth and the notch wing and stuff like that, we noticed that it was all affecting vortices on the wingtip area. But we still had flow attached to the wingtip. It separated first on the inboard side of the wing. So we adopted the lurks, which then produced that primary and secondary vortex over closer to the inboard of the wing to help us keep the flow attached a little longer.
Okay, that's a good explanation. Thank you. It appears to me that the lurks solution may not have been as good as the original model, but again, I'm confused. Maybe this is like okay. Are you guys convinced that that's a good way to go, or?
We're not ready at this moment to make any final conclusions regarding which design is better, and that's why we would like to optimize that design, do a little more investigation, more wind tunnel testing, before confirming or denying, or before making a final decision for or against.
Okay. All right. And then chart 86A. I think you guys said this twice. Both models met all performance requirements. And then at several points in the presentation, you said that the original and modified did not meet the maneuvering requirements at the corner velocity. So those 2 statements seem in conflict.
The requirements per the request for proposal were simply to sustain a 5G and 9G maneuver for 1 minute, but we've had designed in mind during our preliminary design that we would want to meet those at corner velocity to increase our turning and overall performance of the aircraft. The preliminary design did say that we would be able to meet both of these at corner velocity. However, when we did implement the testing, neither model had met those expectations. It does meet the RFP requirement, however, again, does not meet what we had originally predicted and what we had hoped to achieve with the model.
Okay. Okay. It sounds like it doesn't meet the requirement then. That's what I'm hearing based on the data. And the data is what you need to believe in, not necessarily what your prediction is. So somebody mentioned there's no life support system above 50,000 feet, so you won't fly there. Or there's no life support system, so therefore you won't fly above 50,000 feet. Don't you require a life support system below 50,000 feet as well?
We do, but it's simply not the extra oxygen and other concerns that are required at those higher altitudes.
Okay, so just a different life support system.
Pressure systems.
So above 50,000 feet, there's not enough pressure to be able to respirate. So you need a full body pressurization suit in order to be able to respirate. That's not just get enough oxygen. That's to reduce the CO2 that your body needs to exhale.
Okay.
So that's what I meant. I suppose I oversimplified it by saying life support. Of course, there's going to be some level of oxygen, forced oxygen above the required altitudes.
Okay. All right. Thank you for that clarification. Nice job.
Yeah, very nice job. My question was also about the lugs, whether or not you felt like it earned its way onto the airplane. It sounds like you'd like to study that some more. Is that your conclusion, that the performance of before and after the addition of leading edge extension is about the same?
Ultimately, in terms of meeting the performance requirements and again those corner velocity maneuvering that we had hoped, it didn't help tremendously in that regard. But again, we would like to optimize this design before making the final solution.
Thank you.
I'm not much. That doesn't fly well. Okay, just a slight configuration question. After looking at your flow visualization, I can talk, I swear. I noticed that your body obviously is staying attached, but it's also causing an effect on the root of your wing to keep it attached as well, moderately attached as well. It's not as stalled as the tip is. So from a configuration standpoint, have you considered using that particular characteristic, I suppose, to adjust your control surface locations?
I'm not sure I understand.
It's a poorly.
So you're talking about bringing the ailerons inboard so they're out of this effective area of this tip stall.
Right.
No, we haven't looked at that, just because we can only do so many iterations in so little time. So unfortunately that one slipped through. That is a good idea, to say maybe in our control lawn provide in some flap deflection to help at high angles of attack maintain roll stability. Does that answer your question, sir?
Yeah, that's fine.
Okay.
Wasn't a great question in the first place. More yeah, I think that's really it. Most of the questions I had got answered by. Did you take into account? Obviously, you're launching munitions mid-flight, and they are in the body section, but launching them itself has a significant effect on your, well, not significant, but it has an effect on your aircraft's weight. So did you take that into account at all in your controllability?
We did not take that into account during this phase of development.
Okay. Well, great job.
They're not going to like me asking the same question that I asked them yesterday. Is having a sustained capability at your corner velocity one of your requirements?
No, it's not.
Then why is it that you keep saying that you didn't meet your requirements? I don't understand. Name an airplane for me, please, that can sustain its corner velocity. Almost no current fighter can sustain, because you got PCBS gives you a sustained capability, VN diagram gives you your corner velocity. Almost no current fighter airplane can sustain its corner velocity. And we sure couldn't in the F-4, and the F-15 was designed for that, but they can't either, really. It's the same answer I got yesterday. Any other questions?
Good job, guys. This must have been a really cool project to work on, because this is a kind of a dream job project for a lot of aerospace engineers to look up in the sky and see that fighter jet saying, like, I worked on that. Just a real quick thing. Can you go to 68A? I really like they summarized, they met all these requirements. I would prefer there actually being a number comparison though, only because it depends on, because obviously your calculations and predictions will have some sort of a tolerance in real life. You guys have flight plan, so I think if we saw numbers that were really similar to each other, I think that would be a point where you could focus on your conclusions, saying, hey, we might want to adjust this a little bit further away from the required number. So, yeah, well, good job.
Okay, thank you.
Is the bar open? I would ask if there was any more questions, because you know that you could ask them now and they will not have a chance to ask you.
We said this.
between 1.95 and 2.02.
Woo! We couldn't get there before.
That coming directly from one of the mechanical engineer propulsion team that designed the engine for this. Okay, guys, thank you very much.
You said the aircraft stalled, but looking at the CL versus alpha plot, it never really dropped off. It was kind of
The wing stall.
The wing stall. The wing stall, but the aircraft is still producing plenty of lift.
Oh, yeah.
There you go. Yeah.
30 degrees.
And those are the kinds of things I said, guys, you got to stress that because it's still producing lift. You get to higher angles of attack, it's still going. The wing is stalled, but
Do they have to control?
it's a lifting body.
Are they controlled?
You bet.